Hello, everyone, and thank you for joining us to talk about the what we call the Eelgrass Resilience Project in the Great Bay Estuary of New Hampshire and Maine. Formally, you can see the formal title here on the screen: Resilience and Positive Feedbacks, Water Quality Management and Eelgrass Health in the Great Bay Estuary. So the management issue that we're addressing is that eelgrass has declined considerably since 1990s in Great Bay, the National Estuarine Research Reserve in southeastern New Hampshire, and a bit of it's in Maine. So as we all know, there are various potential threats to eelgrass that could be implicated as drivers of this observed eelgrass decline. Water quality, of course, is known to affect eelgrass, but eelgrass can also improve water quality by altering nitrogen, sediment, and other aspects of the system. So our fundamental approach is to ask whether we see signs that the recent reductions in nitrogen loading that have been driven by the declaration of the bay, the designation of the bay as an estuary that's impaired by nitrogen. And so do these recent reductions in nitrogen loading enhance eelgrass resilience, its ability to come back in response to the various ebbs and flows of population abundance you might expect given other drivers? And so to convince you of the eelgrass decline, we can look at this map in the lower left-hand corner. The darker areas, the darker, brighter green are where eelgrass used to be in 1996, and then all the lighter areas are where eelgrass remains in 2016. And so what we can see is a considerable decline in the aerial coverage of eelgrass in the Great Bay Estuary, which is shown here in the overall map. And I should point out we have one of our stakeholders out on the boat looking at eelgrass this summer in one of our outreach and engagement activities. So the eelgrass has declined, and we're asking the following more specific questions and have the following anticipated products from this project. And first, we want to improve the understanding of what drives eelgrass health and resilience in the Great Bay of New Hampshire, and thereby fill some science gaps to help adaptively manage nitrogen in Great Bay. A permit's in place, but it will be reviewed and in a few years' time, and it is an adaptive management approach that has been taken to manage the bay. So some of the anticipated products in terms of the what we're hoping this project will produce include maps of water flow and shear stress at different points in the bay. So how does water move around the bay? How fast? How far? How strong are the currents? Second, analyses of how eelgrass health relates to the nitrogen and light and sediment and colored organic matter and seaweed and plankton that are found across the bay. We'll make new measurements of how eelgrass beds filter nitrogen sediment from the water. And in terms of outreach to the community, we will be preparing what we're calling a quote, so what report. Okay, we've done this good research. What does it tell us about how we might manage the bay? And second important outcome is enhanced K through 12 curriculum resources for local educators. So more specifically, our intended users include really the full realm of, I'll say, is sort of typical possible end users in estuary management. We have our state agency, the New Hampshire Department of Environmental Services, and the US EPA. We have a number of municipalities whose nitrogen outputs, point source from their wastewater treatment plants, are regulated. Those are among our users. We have local watershed and NGO groups, such as the Conservation Law Foundation, who are very actively engaged in the project. And then we have local education groups and schools, K through 12, that are engaged in the project. So if we look specifically at some of those education activities, we have what's called a traveling trunk, which is a bunch of show and tell specific things about eelgrass, like models of eelgrass and actual strands of eelgrass, descriptions of how eelgrass works in the environment, and teacher workshops to get the teachers able to use this traveling trunk in presentations. For a more general public audience, we have visitor center enhancements and some public outreach activities such as Lunch and Learn that's been proposed. Now, our technical and collaborative approach, in terms of technical, we're building on existing sampling by expanding to include water quality parameters, conducting more detailed assessment of hydrologic flow paths, and measuring rates of nitrogen removal processes, specifically denitrification primarily, as well as measures of eelgrass health. And in terms of the collaborative approach, we're using extensive collaboration and coordination with NERR staff, multiple scheduled meetings through the course of the project with our project advisory committee, and other meetings with the whole research team. We have a schedule here. We're not really going to go through it in detail, but if you want to, you can pause and look at the meetings. We're on track and have completed the meetings that we planned, and we're holding as many as we can in person, but we're realizing that Zoom may also have some benefits, so we're doing a mix. We look specifically at our two research questions. The first is, does eelgrass health vary spatially in response to variability in water residence times, bed shear stress, algae, epiphytes, and water quality? So does the physical environment, or how does the physical environment affect eelgrass? And then research question two is almost the flip side of that, where we ask, well, does the nitrogen and the sediment filtration and other aspects of eelgrass function, do they vary along hydrodynamic flow paths that span unvegetated areas to eelgrass rich areas? So we're looking at how the eelgrass affects its own physical environment. And we won't go into any of the details of that, just suffice it to say, we've been out on the water deploying the drifters that can tell us how the water's moving in response to currents, tidal currents and winds. And you can see on the right some pictures of where the green and the red buoys have traveled during the course of the experimental deployments. Some the computer output of the velocity fields and directional fields that are produced in the bay, and some idea of how long particles stay in the day. How many hours do they do if we introduce a set of particles in the bay in the hydrodynamic model? How long do they stay? And so we can see here it's up to about 700 hours or so. Now, in terms of denitrification, we have a grad student who's one of her PhD thesis chapters is about the denitrification along flow transects through the beds. And this involves some what are called push-pull experiments with the membrane inlet mass spectrometer, or MIMS. And so we are trying to advance the state of science, understanding how eelgrass affects its own environment through the denitrification using this method. So finally, just to summarize the management issues, the benefits with these specific products and outcomes, we hope to understand whether eelgrass is likely to bounce back in the bay with the reduced nitrogen input that has just started to get underway. We hope to engage stakeholders in a way that builds trust in the scientific process and thus the scientific outputs that come from our project. And third, with our education and outreach activities, we hope to expand public awareness of the role of eelgrass in maintaining the health of Great Bay. Thank you very much.